As you sit here watching this video, something invisible is passing through your body. Not one particle. Not 100. Trillions upon trillions of invisible particles are streaming through your flesh, your bones, your brain, every single second. They pass through the walls of your house. They pass through the earth itself as if it were not even there. They have been doing this since before you were born, since before the earth existed, since before the sun ignited for the first time 4.5 billion years ago. And we have no idea what they are. We cannot see them, we cannot touch them, we cannot catch them in any detector ever built by human hands. But we know they are real. We know they are real, because without them, you would not exist. The earth would not exist. The sun would not exist. No galaxy in the entire observable universe would exist. Everything you have ever known, everything you have ever loved, every star you have ever seen in the night sky, all of it exists because of something invisible. Something we have named but never identified, something that makes up 85% of all the matter in the universe. We call it dark matter. And that name, that simple two-word name, hides one of the deepest and most humbling mysteries in the entire history of human knowledge. But here is where the story gets truly strange. Here is where it crosses the line from mysterious into almost unbelievable. In 2016, a team of astronomers pointed an unusual telescope at a patch of sky in the direction of a massive galaxy cluster called the Coma Cluster, roughly 330 million light-years from Earth. They were looking for faint objects so dim that ordinary telescopes would miss them entirely. And they found something that shook the foundations of astrophysics. They found a galaxy almost as massive as our own Milky Way. A galaxy spanning tens of thousands of light-years across. But this galaxy was almost entirely invisible. It had almost no stars, almost no gas, almost no dust, almost nothing that we would normally associate with a galaxy. When they calculated its total mass, they discovered something that made no sense. 99.99% of this galaxy was made of dark matter. Let that number settle in your mind. 99.99%. That means if you could somehow weigh this entire galaxy, put it on some cosmic scale, only 1/100% of its weight would come from anything visible. The rest, the overwhelming, dominating, almost totality of its existence, is made of something we cannot explain. They named this galaxy Dragonfly 44, and to this day we cannot fully explain how it exists. Now, before we dive deep into this mystery, I want you to think about something. Think about the night sky. When you look up on a clear night, you see thousands of stars. You see the faint band of the Milky Way stretching across the darkness. You feel like you are seeing the universe. But you are not. You are seeing less than 5% of what is actually out there. 95% of the universe is invisible to your eyes, invisible to every telescope ever built, invisible in a way that challenges our very definition of reality. And Dragonfly 44 is perhaps the most extreme example of this invisible universe that we have ever found. So let us begin this journey. Let us start from the very beginning. From the first moment a human being realized that the universe was hiding something enormous from us, and let us follow that thread all the way to the edge of what we know and the terrifying boundary of what we do not. If this journey excites you, if this kind of deep exploration is what you come here for, then hit that like button right now, subscribe to this channel, and ring that bell icon, because what you are about to hear over the next 90 minutes will fundamentally change the way you look at the night sky. Let us go back to 1933. The place is the California Institute of Technology. The person is a Swiss astronomer named Fritz Zwicky, and he is one of the most brilliant and simultaneously most difficult human beings in the history of science. Zwicky was abrasive. He was rude. He called his colleagues spherical bastards, claiming they were bastards no matter which direction you looked at them from. But beneath that impossible personality was a mind that saw things other people missed. Zwicky was studying the Coma Cluster, the same galaxy cluster where Dragonfly 44 would be found more than 80 years later. He was measuring how fast the galaxies in this cluster were moving. He used their redshifts, the stretching of their light caused by their motion, to calculate their velocities, and when he added up all the visible matter in the cluster, all the stars and gas he could see, he found something deeply troubling. The galaxies were moving too fast. Way too fast. Based on the visible mass of the cluster, the galaxies should have been moving at a certain speed, a speed dictated by the gravitational pull of everything he could see. But they were moving far faster than that, so fast that the cluster should have torn itself apart billions of years ago. The gravity of the visible matter was nowhere near strong enough to hold these galaxies together. Something else was there. Something massive. Something invisible. Zwicky calculated that the cluster must contain at least 400 times more mass than what was visible. He called this unseen mass-dunkel mattery. Dark matter. The scientific community largely ignored him, partly because his personality made it easy to dismiss him, partly because the idea was so radical that it seemed easier to assume he had made an error. And so for nearly 4 decades, the concept of dark matter sat in the margins of astrophysics, an uncomfortable idea that most people preferred not to think about. Then came Vera Rubin. In the 1970s, Rubin was an astronomer at the Carnegie Institution of Washington, and she was studying something seemingly straightforward. She was measuring how fast stars rotated around the centres of spiral galaxies. According to Newtonian gravity and everything we understood about orbital mechanics, stars at the outer edges of galaxies should move slower than stars near the centre. This is the same principle that makes Mercury orbit faster than Neptune. The farther you are from the central mass, the weaker the gravitational pull, the slower you should move. But that is not what Rubin found. She found that stars at the outer edges of galaxies were moving just as fast as stars near the centre. In galaxy after galaxy, the rotation curves were flat. The stars at the edges were orbiting at velocities that should have flung them out of the galaxy entirely. There was not enough visible mass to hold them in their orbits, unless there was something else there, something enormous, something invisible, something surrounding the galaxy in a vast extended halo. Rubin had independently confirmed what Zwicky had suggested 4 decades earlier. Dark matter was real. It was not an error. It was not an artifact. It was a fundamental feature of the universe, and the amount of it was staggering. For every kilogram of normal matter in the universe, there are roughly 5.5 kilograms of dark matter. It outweighs everything you can see by a factor of nearly 6 to 1. Every galaxy, including our own Milky Way, is embedded in a vast halo of dark matter that extends far beyond the visible stars. Our galaxy is like a luminous city floating in an ocean of invisible mass, and that invisible ocean is not just sitting there passively. It is the reason the city exists in the first place. To understand why dark matter is so fundamental, you need to go back to the very beginning of the universe, not millions of years ago, not billions. Go back 13.8 billion years to the first moments after the Big Bang. In those earliest moments, the universe was a nearly uniform soup of energy and particles. Nearly uniform, but not perfectly uniform. There were tiny, almost imperceptible variations in density. Regions where matter was ever so slightly more concentrated than average, and regions where it was ever so slightly less concentrated. These variations were quantum fluctuations, stretched to cosmic scales by the rapid expansion of inflation. And here is where dark matter enters the story in the most profound way possible. Normal matter in the early universe could not clump together on its own. It was too hot. The photons, the particles of light, were constantly colliding with the charged particles of normal matter, preventing them from gravitating together. It was like trying to build a sandcastle while someone constantly blew the sand away. But dark matter does not interact with light. Dark matter does not care about photons. So while normal matter was being buffeted and scattered by radiation, dark matter was quietly, invisibly, gravitating together. It was falling into those tiny density variations and amplifying them. It was building the scaffolding of the universe. Dark matter formed vast structures, cosmic filaments and nodes and sheets, creating what we now call the cosmic web. And later, when the universe cooled enough for normal matter to decouple from radiation, That normal matter fell into the gravitational wells that dark matter had already prepared. It collected in the densest regions, cooled further, collapsed, and began forming stars and galaxies. Every galaxy you see in the night sky formed inside a dark matter halo. Every star, every planet, every living thing on every planet owes its existence to dark matter. Without it, the universe would be a diffuse, featureless fog of gas and radiation, with no structure, no galaxies, no stars, no planets, and no one to wonder about any of it. This is the cosmic pie chart that defines our reality. 68.3% of the universe is dark energy, the mysterious force driving the accelerating expansion of space. 26.8% is dark matter, the invisible mass that built the scaffolding for everything we see. And 4.9% is ordinary baryonic matter. That is you. That is me. That is the sun and the earth and every star in every galaxy. We are the cosmic rounding error. We are the rare, precious, improbable foam on an ocean of darkness. And the fact that we exist at all, that we can sit here and contemplate this, is one of the most astonishing things about the universe. Now, with all of this as background, let us return to Dragonfly 44. Let us return to this ghost galaxy, this cosmic phantom, this object that is 99.99% invisible. And let us start with the instrument that found it, because the story of Dragonfly 44 begins not with a giant observatory on a mountaintop, but with an array of ordinary camera lenses in a farmer's field in New Mexico. Peter van Dokkum is a Dutch astronomer based at Yale University. Roberto Abraham is a Canadian astronomer at the University of Toronto. In the early 2010s, they shared a frustration that had been nagging at astronomers for years. They knew that the universe was full of objects that were too faint, too diffuse, too spread out for conventional telescopes to detect. Traditional telescopes are extraordinary machines. They can see objects billions of light years away. They can resolve individual stars in distant galaxies. But they have a weakness. When light enters a conventional telescope, it bounces around inside the optical system, scattering off internal surfaces, creating a faint haze that washes out extremely low surface brightness objects. It is like trying to see a firefly in a room full of fog. The firefly is there, but the scattered light hides it. Van Dokkum and Abraham had an idea. Instead of building a bigger, more powerful conventional telescope, what if they built something completely different? What if they used commercially available Canon telephoto lenses, the kind of lenses used by wildlife photographers and sports photographers, but coated with a special nano-fabrication coating designed to virtually eliminate internal light scatter? These lenses, the Canon 400mm f/2.8, were specifically engineered to minimize reflections and ghosting. They were, by their very design, ideal for detecting the faintest, most diffuse light sources in the sky. They started with 3 lenses, then 8. Then they kept expanding. They mounted these lenses on a single tracking platform, all pointing at the same patch of sky, combining their light-gathering power. They called it the Dragonfly Telephoto Array because the front of the array, with its cluster of round lens elements, looked like the compound eye of a dragonfly. It was not the most expensive astronomical instrument ever built. It was not the largest or the most technologically complex. But for its specific purpose, for detecting ultra-low surface brightness objects, it was the best instrument in the world. Nothing else could see what Dragonfly could see. In 2014 and 2015, Van Dokkum and Abraham pointed the Dragonfly Array at the Coma Cluster. This was a deliberate choice. The Coma Cluster is one of the largest, most massive and most well-studied galaxy clusters in the nearby universe. It contains over 1,000 known galaxies, and it was the very same cluster where Fritz Zwicky had first proposed the existence of dark matter more than 80 years earlier. The team was looking for ultra-diffuse galaxies, or UDGs, a class of galaxies that had only recently been recognised. These are galaxies that are physically large, sometimes as big as the Milky Way, but incredibly faint. Their surface brightness is so low that they are nearly invisible against the background glow of the night sky. For decades, astronomers had occasionally stumbled upon these ghostly objects, but they were considered curiosities. Oddities, not worthy of serious attention. The Dragonfly team was about to change that completely. They found 47 ultra-diffuse galaxies in the Coma Cluster. 47 galaxies that had been hiding in plain sight, too faint for other telescopes to notice. It was already a remarkable discovery. But one of these 47 galaxies was different from the others. One of them was special. It was designated Dragonfly 44, the 44th object in their catalogue, and it was about to become one of the most discussed objects in modern astrophysics. At first glance, Dragonfly 44 did not look like much. It was a faint smudge of light, barely distinguishable from the noise in their images. It appeared to be a diffuse collection of old, dim stars, stretched across a region about 15,000 light-years in radius. That is a big galaxy. Not as big as the Milky Way, which stretches about 26,000 light-years from centre to edge, but substantial. The problem was immediately obvious. A galaxy of that size should have billions of stars. The Milky Way, which is somewhat larger, has between 200 billion and 400 billion stars. But Dragonfly 44 appeared to have only about 100 million stars. That is 1,000 times fewer stars than the Milky Way in a galaxy that was nearly the same size. Something was wrong. Something was holding this galaxy together, keeping its sparse collection of stars from flying apart, and that something was not visible. The team needed to confirm their suspicion. They needed to measure the mass of Dragonfly 44 directly, not by counting its stars, but by measuring how fast those stars were moving. This is the same basic principle that Zwicky and Rubin had used. If you know how fast the components of a system are moving, you can calculate how much gravitational force is needed to keep them bound together. And from that, you can calculate the total mass. But there was a problem. Dragonfly 44 was incredibly faint. Its stars were dim and diffuse. Measuring the velocities of individual objects within the galaxy would require one of the most powerful telescopes on Earth and an enormous amount of observation time. So the team went to the Keck Observatory on the summit of Mauna Kea in Hawaii. The Keck telescopes are among the largest optical telescopes in the world, with primary mirrors 10 meters across. The team used Keck to perform spectroscopic observations of Dragonfly 44, measuring the Doppler shifts of light from stars and globular clusters within the galaxy to determine their velocities. It took 33.5 hours of total exposure time. 33.5 hours of one of the world's most powerful telescopes staring at a single faint smudge of light, and the results were extraordinary. The velocity dispersion of Dragonfly 44, the measure of how fast its stars are moving in random directions, was approximately 47 kilometers per second. That number might not mean much to you on its own, so let me put it in context. For a galaxy with only 100 million stars, a velocity dispersion of 47 kilometers per second is absurdly high. If the only mass in Dragonfly 44 were its visible stars, those stars would be moving far too fast to remain bound to the galaxy. They would fly apart. The galaxy would dissolve. The fact that it has held together for billions of years means there must be an enormous amount of unseen mass providing the gravitational glue. When the team did the calculation, when they used the velocity dispersion to estimate the total mass of Dragonfly 44, the number came out to approximately 1 trillion solar masses. 1 trillion. That is almost identical to the estimated total mass of the Milky Way itself. But the Milky Way achieves that mass with hundreds of billions of visible stars, vast reservoirs of gas, and a substantial dark matter halo that makes up about 85% of its total mass. Dragonfly 44 achieves essentially the same total mass with almost nothing visible. The ratio of dark matter to visible matter is not 85%. It is not 90%. It is not 95%. It is 99.99%. Let me help you visualize this. Imagine you are standing inside Dragonfly 44. Imagine you are on a hypothetical planet, orbiting one of its sparse, dim stars. You look up at the night sky. In the Milky Way, from a dark location, you can see several thousand stars with the naked eye, and the Milky Way itself stretches as a luminous band across the heavens. In Dragonfly 44, you would see almost nothing, a handful of faint, scattered stars. The sky would be overwhelmingly dark, yet you would feel gravity. Your planet would orbit its star normally. The galaxy around you would be gravitationally bound, held together, structured. You would be living in a galaxy that is almost entirely invisible, held together by a substance you cannot see, cannot touch, cannot detect with any instrument on your hypothetical world. The universe around you would be mostly dark, and not the kind of dark that simply means an absence of light. A deeper kind of dark, a dark that has mass, a dark that has gravity, a dark that shapes the very structure of reality. You would be living in a house where 99.99% of the building materials are invisible. The paper was published in 2016 in the Astrophysical Journal Letters. The lead author was Peter van Dokkum, and it sent shockwaves through the astronomical community. Not because dark matter was unexpected in galaxies, every galaxy we know of has dark matter, but because no one had ever found a galaxy where the imbalance was this extreme. In the Milky Way, dark matter makes up about 85% of the total mass. In most galaxies, it is somewhere between 80 and 95%. Even in most ultra-diffuse galaxies, dark matter accounts for 95 to 98% of the total mass. But 99.99%? That was off the charts. That was a galaxy that is functionally a dark matter object with a tiny sprinkling of stars. It raised immediate and profound questions. How could such a galaxy form? What happened to all the normal matter that should be there? Why did it fail to form stars? And most troublingly, did our models of galaxy formation even allow for something like this? There was also something else about Dragonfly 44 that deepened the mystery, something that involved tiny ancient objects called globular clusters. Globular clusters are dense, spherical collections of stars, typically containing hundreds of thousands to millions of stars packed into a ball just a few dozen light-years across. They are among the oldest objects in the universe, with most of them having formed more than 10 billion years ago. In the Milky Way, we know of about 150 globular clusters. And here is the key fact. The number of globular clusters a galaxy possesses tends to correlate very strongly with the galaxy's total mass, not its visible mass, but its total mass including dark matter. This is a well-established relationship in astronomy. More massive galaxies tend to have more globular clusters. When the Dragonfly team examined their images of Dragonfly 44, they counted approximately 94 globular clusters. 94. For a galaxy with only 100 million stars, that is an extraordinary number. A galaxy with that few stars would typically be expected to have perhaps 10 or 20 globular clusters, but 94 is in the range expected for a galaxy with a total mass of about 1 trillion solar masses. The globular cluster count independently confirmed the velocity dispersion measurement. Both methods pointed to the same conclusion. Dragonfly 44 is almost entirely dark matter. But science does not stand still, and not everyone was convinced. In 2020, a team led by Taimoor Saifulahi published a reanalysis of the globular cluster population of Dragonfly 44. Using deeper imaging data from the Hubble Space Telescope, they argued that many of the objects originally identified as globular clusters might actually be background galaxies or other contaminants. Their revised count was much lower, perhaps around 20 globular clusters rather than 94. If correct, this would significantly reduce the independent confirmation of Dragonfly 44's extreme mass. It would not eliminate the dark matter problem entirely, because the velocity dispersion measurement still stood, but it would weaken one of the supporting pillars. The original team pushed back. They argued that the reanalysis used different methods and different assumptions, and that the original count was robust. The debate went back and forth in the literature, with different groups using different techniques and arriving at different conclusions. As of the most recent analyses, the situation remains somewhat uncertain. The globular cluster count of Dragonfly 44 is somewhere between 20 and 94, depending on who you ask and which dataset they use. But even the lower estimates, combined with the velocity dispersion, still point to an extremely dark matter-dominated galaxy. The exact number, whether it is 98% or 99.99%, is debated, but the fundamental strangeness of Dragonfly 44 is not in question. And now let me tell you about something even stranger. something that seems to contradict Dragonfly 44 entirely, something that appeared in the scientific literature just 2 years after Dragonfly 44's mass was published, and it came from the very same team. In March 2018, Peter van Dokkum and his collaborators published a paper in the journal Nature announcing the discovery of a galaxy called NGC 1052 DF2. Like Dragonfly 44, DF2 is an ultra-diffuse galaxy. It is large, dim and diffuse, but unlike Dragonfly 44, DF2 appeared to have almost no dark matter at all. The team measured the velocities of 10 bright globular clusters within DF2 and found that they were moving very slowly. So slowly that the visible mass of the galaxy, its stars and globular clusters, was sufficient to account for all the gravitational force needed to keep them in their orbits. There was no need for any additional dark matter. The mass-to-light ratio was consistent with a galaxy made almost entirely of ordinary baryonic matter. This was astonishing. If Dragonfly 44 was 99.99% dark matter, DF2 appeared to be essentially 0% dark matter. The two galaxies represented opposite extremes of a spectrum that no one had previously imagined could be so wide, and the discovery of DF2 was followed, in 2019, by the discovery of yet another galaxy with apparently no dark matter. NGC 1052 DF4. Same team. Same conclusion. Another galaxy where the visible mass accounts for everything, with no invisible mass required. Now you might think that the discovery of galaxies without dark matter would undermine the case for dark matter's existence. If galaxies can exist without it, maybe it was never there in the first place. Maybe the gravitational anomalies we see in other galaxies are due to something else, modified gravity perhaps, rather than an invisible substance. But here is the beautiful irony. The existence of DF2 and DF4 actually strengthens the case for dark matter. It strengthens it enormously, and the reason is subtle but profound. Think about it this way. If dark matter is a real substance, a real particle, something that exists independently of the stars and gas in a galaxy, then it should be possible, in principle, to separate dark matter from visible matter. If two galaxies collide, or if a galaxy passes through a dense cluster environment, gravitational tidal forces could strip the dark matter halo from the visible galaxy, or strip the visible matter from the dark matter halo. You could end up with concentrations of dark matter that have very few stars, like Dragonfly 44. Or you could end up with collections of stars that have very little dark matter, like DF2 and DF4. Both outcomes are possible if dark matter is a real substance, but if the gravitational anomalies were caused by modified gravity, by a change in the laws of physics rather than an invisible substance, then you could never separate them. Modified gravity would affect all matter equally, everywhere. You could not have a galaxy where the modification is absent. The existence of galaxies both with extreme dark matter and with essentially no dark matter is a powerful argument that dark matter is a real separable substance, not a modification of gravity. And indeed, when astronomers looked more closely at DF2 and DF4, they found evidence for exactly this kind of separation. Both galaxies are located near a massive elliptical galaxy called NGC 1052, and DF4 in particular showed signs of tidal disruption. Its stars were being stretched and distorted by the gravitational pull of NGC 1052. It appeared that the dark matter halo of DF4 had already been largely stripped away by tidal interactions, leaving behind a galaxy made almost entirely of visible matter. The dark matter was not absent from the universe. It had simply been pulled away from this particular galaxy. It was somewhere else. And this process, this separation of dark matter from visible matter, is something we have observed in an even more dramatic context. The Bullet Cluster. The Bullet Cluster is one of the most important observations in the history of dark matter research. It consists of two galaxy clusters that collided with each other roughly 150 million years ago. When galaxy clusters collide, the individual galaxies within them, being relatively small and widely spaced, mostly pass through each other without interacting. But the hot gas that fills the space between galaxies in a cluster, the intracluster medium, does interact. The gas from the two clusters collides, slows down and gets stuck in the middle, piling up between the two clusters. We can see this gas because it emits X-rays, and the Chandra X-ray Observatory mapped its distribution beautifully. But here is the key observation. Using gravitational lensing, astronomers also mapped where the majority of the mass in the system was located. Gravitational lensing is the bending of light from background galaxies by the gravity of foreground mass. By measuring how much the light from background galaxies is distorted, you can map the distribution of mass in the foreground, regardless of whether that mass is visible or invisible. And the lensing maps showed that the majority of the mass in the bullet cluster was not where the gas was. The mass had passed right through the collision point and was now located on either side, coincident with the galaxies, but separated from the gas. The mass had behaved like something that does not interact with ordinary matter. It had passed through the collision like a ghost, unaffected by the violent smash-up of gas in the middle. This is exactly what dark matter should do. Dark matter does not interact via the electromagnetic force. It does not collide with gas. It just passes through. The Bullet Cluster observation, published by Douglas Clow and collaborators in 2006, is considered by many to be the single most convincing piece of evidence that dark matter is a real substance and not a modification of gravity. So let us take stock of where we are. Dark matter is real. It is a substance. It can be concentrated, as in Dragonfly 44. It can be stripped away, as in DF2 and DF4. It can be separated from normal matter in collisions, as in the Bullet Cluster. It makes up about 85% of all matter in the universe. It built the scaffolding on which galaxies formed. Without it, we would not exist. And yet, despite nearly a century of searching, we have never directly detected a single particle of dark matter. We do not know what it is made of. We do not know how many types of dark matter particles there are. We do not know if dark matter particles interact with each other. We are, in a very real sense, in the position of someone who can see the footprints of an animal in the snow, can trace its path through the forest, can see the branches it pushed aside, the prey it captured, the den it built, but has never actually seen the animal itself. We know dark matter is there. We know what it does, but we have no idea what it looks like. This brings us to one of the most fascinating and frustrating aspects of modern physics, the search for dark matter particles. For decades, the leading candidate for dark matter has been a class of hypothetical particles called WIMPs, weakly interacting massive particles. The idea behind WIMPs is elegant. If dark matter is made of particles that are heavy, perhaps tens or hundreds of times the mass of a proton, and that interact only through the weak nuclear force and gravity, then two remarkable things happen. First, you naturally get the right amount of dark matter in the universe. The conditions of the early universe would produce WIMPs in exactly the right abundance to match observations. This coincidence, known as the WIMP miracle, made WIMPs the most compelling dark matter candidate for many years. Second, WIMPs should occasionally interact with ordinary matter. Very rarely, but occasionally. If you build a sensitive enough detector, you should be able to catch a WIMP bouncing off an atomic nucleus. The rate would be incredibly low. Perhaps a few interactions per year in a ton of detector material, but it should be detectable. And so the search began. Deep underground, in mines and tunnels around the world, physicists built extraordinary detectors. They went underground to escape the constant rain of cosmic rays from space, which would swamp any potential dark matter signal. The deeper you go, the more cosmic rays are absorbed by the rock above, and the cleaner your detector becomes. In the Sanford Underground Research Facility in South Dakota, nearly a mile below the surface of the Earth, a detector called LUX, the Large Underground Xenon Experiment, began searching for WIMPs in 2013. It used a tank of ultra-pure liquid xenon, cooled to minus 100 degrees Celsius. The idea was simple in principle. If a WIMP particle from the dark matter halo of the Milky Way happened to strike a xenon nucleus, it would produce a tiny flash of light and a small burst of electric charge. Sensitive photomultiplier tubes at the top and bottom of the detector would capture this signal. LUX ran for years. It found nothing. No confirmed dark matter signal. It set stringent limits on the properties of WIMPs, ruling out large regions of the parameter space where WIMPs could exist. But no detection. LUX was followed by a more powerful experiment called LUX Zeppelin, or LS, which used 10 tons of liquid xenon instead of LUX's original amount. In Italy, beneath the Gran Sasso mountain, the Xenon collaboration built a series of increasingly large detectors, culminating in Xenonont. In China, the Panda X experiment pursued the same goal. All of these experiments are marvels of engineering. The xenon must be purified to an extraordinary degree, removing even trace amounts of radioactive contaminants that could mimic a dark matter signal. The detectors must be shielded from every possible source of background noise. The analysis techniques must be sophisticated enough to distinguish a genuine dark matter interaction from the countless other particle interactions that occur even deep underground. And yet, despite all this effort, despite decades of searching and billions of dollars of investment, no direct detection of dark matter has been confirmed. The parameter space where WIMPs can hide is shrinking. The experiments are approaching a fundamental limit called the neutrino floor, below which the detectors will start seeing neutrino interactions from the sun and the atmosphere, creating an irreducible background that will be extremely difficult to distinguish from dark matter. If WIMPs are not found before the neutrino floor is reached, it will not necessarily mean WIMPs do not exist. They could simply have properties that make them even harder to detect. But it will be a significant blow to the WIMP paradigm, and it will force physicists to seriously consider alternative candidates. And there are alternatives. One of the most exciting is the axion. Axions were not originally proposed as dark matter candidates. They were proposed in the late 1970s to solve an entirely different problem in particle physics, the strong CP problem, which is a technical issue involving the symmetry properties of the strong nuclear force. But it was soon realized that if axions exist, they could be produced in the right quantities in the early universe to account for dark matter. Axions would be extraordinarily light, perhaps 1 trillion times lighter than an electron. They would interact with ordinary matter even more weakly than WIMPs. But they have one potentially detectable property. In the presence of a strong magnetic field, an axion can convert into a photon, a particle of light. If you build a strong enough magnetic field and a sensitive enough microwave detector, you might be able to catch this conversion happening. The axion dark matter experiment, ADMX, based at the University of Washington, has been searching for axions using exactly this technique. It consists of a powerful superconducting magnet surrounding a resonant cavity, all cooled to temperatures just above absolute zero to minimize noise. As of the most recent results, ADMX has not found axions, but it has begun probing the most theoretically favored mass ranges. The search is ongoing, and the experimental sensitivity continues to improve. Then there are sterile neutrinos, hypothetical heavier cousins of the familiar neutrinos, which interact even more weakly than ordinary neutrinos. There are primordial black holes that could have formed in the extreme conditions of the very early universe, not from collapsing stars, but from density fluctuations in the primordial plasma. There is self-interacting dark matter, where dark matter particles can collide with each other, but not with ordinary matter. There is fuzzy dark matter, made of particles so light that their quantum wavelength is comparable to the size of a galaxy, causing them to behave more like waves than particles on cosmic scales. And there are even more exotic possibilities. A whole dark sector, with its own forces and its own complexity, a parallel world of invisible physics operating alongside our visible universe. Every one of these candidates would produce a slightly different universe on small scales. WIMPs would create dense, cuspy dark matter halos with lots of small substructure. Fuzzy dark matter would create smoother, chord halos with less substructure. Self-interacting dark matter would create halos whose central densities depend on their history of interactions. And this is where galaxies like Dragonfly 44 become so valuable. By studying the detailed properties of extreme objects, the most dark matter-dominated and the least dark matter-dominated galaxies we can find, we can potentially distinguish between these candidates. The internal structure of Dragonfly 44, the distribution of its dark matter, the properties of its globular clusters, the velocities of its stars, all of these contain clues about the nature of dark matter itself. Dragonfly 44 is not just a curiosity, it is a laboratory, a cosmic laboratory for studying the physics of the invisible. Now I want to take you deeper into the question of how Dragonfly 44 formed. This is not a settled question. There are multiple hypotheses, and each tells us something different about the interplay between dark matter and visible matter in the universe. Let me walk you through the leading ideas. The first hypothesis is what we might call the failed galaxy model. In this picture, the dark matter halo of Dragonfly 44 formed perfectly normally. It assembled in the early universe through the standard process of hierarchical merging, smaller halos combining to form larger ones, eventually reaching a mass of about 1 trillion solar masses. So far, this is exactly what happened to the halo that would become the Milky Way. But then, something went differently. In the Milky Way's halo, gas cooled efficiently, collapsed to the centre of the halo, and began forming stars at a prodigious rate. Star formation continued for billions of years, building up the hundreds of billions of stars we see today. In Dragonfly 44's halo, something prevented this from happening. Something stopped the star formation process in its tracks, very early, after only a tiny fraction of the available gas had been converted into stars. What could do this? There are several possibilities. One is early stellar feedback. The first generation of stars to form in Dragonfly 44 might have been particularly massive and energetic. When massive stars die, they explode as supernovae, releasing enormous amounts of energy into their surroundings. If enough supernovae went off in a short period of time, the combined blast could have heated the remaining gas to such high temperatures that it expanded out of the galaxy entirely, blown away into intergalactic space. With no gas left, star formation would cease. The galaxy would be left with only the stars that had already formed, embedded in its massive dark matter halo. This is a process known to happen in dwarf galaxies. The question is whether it could work in a halo as massive as Dragonfly 44's. In very massive halos, the gravitational potential well is deep enough that even supernova-heated gas has difficulty escaping. But if the star formation was concentrated in a very short, intense burst, and if the conditions were just right, it might be possible. Some cosmological simulations, including runs of the Fire Simulation Suite and the Nihao project, have managed to produce Dragonfly 44-like objects through this mechanism. But they are rare in the simulations, which is consistent with the fact that they are rare in the real universe. A second possibility involves the environment. Dragonfly 44 lives in the Coma Cluster, one of the most massive and hostile environments in the nearby universe. Galaxy clusters are filled with extremely hot gas, the intracluster medium, which has temperatures of tens of millions of degrees. When a galaxy moves through this medium, the ram pressure of the hot gas can strip the galaxy's own gas away, like wind stripping leaves from a tree. This process, called ram pressure stripping, is observed in many cluster galaxies and can dramatically reduce or completely halt star formation. If the progenitor of Dragonfly 44 fell into the Coma Cluster early in its history, when it still had gas but had only formed a small number of stars, the cluster environment could have stripped away all of its remaining gas, permanently quenching star formation. A third possibility is related to the physics of the early universe itself. During the epoch of rhionization, roughly 1 billion years after the Big Bang, the first stars and galaxies produced enough ultraviolet radiation to ionize the hydrogen gas throughout the universe. This flood of UV radiation heated the intergalactic gas, making it much harder for that gas to cool and collapse into low-mass dark matter halos. Halos below a certain mass threshold, roughly 10 billion solar masses, would have had their gas effectively boiled away by reionization. But Dragonfly 44's halo is much more massive than this threshold, at about 1 trillion solar masses, so reionization alone cannot explain it. However, reionization could have played a contributing role, reducing the efficiency of gas accretion onto the halo in the early universe, making it easier for other mechanisms like stellar feedback to subsequently blow out the remaining gas. A fourth hypothesis involves the angular momentum of the halo. Dark matter halos are not static objects. They are spinning, slowly, with a property called the spin parameter that describes how much angular momentum they have relative to their mass and size. Most halos have similar spin parameters, but some, by chance, spin faster than average. In a fast-spinning halo, the gas that falls in acquires a lot of angular momentum. This angular momentum prevents the gas from collapsing efficiently to the centre of the halo. Instead of concentrating into a dense, star-forming cloud, the gas spreads out into a diffuse, extended disk that is too thin and too low density to form many stars. The result would be a galaxy with very few stars spread over a very large area, embedded in a massive dark matter halo. This is the high-spin hypothesis for UJ formation, and it naturally produces objects with properties similar to Dragonfly 44. The truth may be a combination of all of these factors. Perhaps Dragonfly 44 started as a high-spin halo, making its gas inherently reluctant to form stars. Then early supernovae from the first small burst of star formation heated and expelled much of the remaining gas. Then, as the galaxy fell into the Coma Cluster, ram pressure stripping finished the job, removing whatever gas was left. The end result would be a massive dark matter halo with only a tiny remnant of visible matter, a galaxy that is 99.99% dark. It is a story of potential unrealized, of a galaxy that had all the raw materials to become something like the Milky Way, but was prevented by a conspiracy of circumstances from ever fulfilling that potential. And this is where the story of Dragonfly 44 connects to something even larger. The Coma Cluster itself, and the deeply poetic fact that this cluster, this particular collection of galaxies, has been at the centre of the dark matter story from the very beginning. When Fritz Zwicky first proposed the existence of dark matter in 1933, he was studying the Coma Cluster. He was measuring the velocities of galaxies within it, and finding that they were moving too fast for the visible mass to hold them together. And now, more than 80 years later, the most extreme dark matter galaxy ever found resides in that very same cluster. There is a symmetry to this, a narrative elegance that science rarely provides. The Coma Cluster is where dark matter was born as a concept, and it is where dark matter reaches its most extreme known expression. The Coma Cluster is a colossus among galaxy clusters. It is located approximately 330 million light-years from Earth, in the direction of the constellation Coma Berenices. It contains over 1,000 identified galaxies, ranging from giant ellipticals at its centre to spirals, dwarfs, and now we know, dozens if not hundreds of ultra-diffuse galaxies like Dragonfly 44. The total mass of the cluster is approximately 700 trillion solar masses. That is 700 trillion times the mass of our Sun. And the vast majority of that mass, roughly 80 to 90%, is dark matter. The cluster environment is brutal. The space between galaxies in the Coma Cluster is filled with gas heated to temperatures exceeding 100 million degrees Kelvin. This gas, the intracluster medium, emits copious amounts of X-rays and was one of the first things detected by X-ray telescopes when they were pointed at galaxy clusters. Any galaxy moving through this medium experiences enormous ram pressure, and over time, this pressure strips galaxies of their gas, transforming them from active, star-forming systems to passive, dead objects. The Coma Cluster is a graveyard for star formation, and Dragonfly 44, with its ancient red stars and complete absence of ongoing star formation, is one of its most dramatic tombstones. But the Coma Cluster has also given us something else. When the Dragonfly team published their initial survey results in 2015, they reported finding 47 ultra-diffuse galaxies. Subsequent surveys, using the Subaru telescope and other instruments, found hundreds more. The Coma Cluster turned out to be teeming with these ghostly objects. They had been there all along, hiding in the glare of brighter galaxies, too faint and too diffuse for conventional surveys to detect. The discovery of UDGs in the Coma Cluster, and subsequently in other galaxy clusters and even in isolation in the field, opened up an entirely new chapter in our understanding of galaxy diversity. And here is something I want you to think about. If the Coma Cluster contains hundreds of ultra-diffuse galaxies, and if some of these galaxies are 95, 98, or 99% dark matter, then how many even fainter galaxies are out there that we have not found yet? How many objects exist that are so dark, so devoid of stars, that even the Dragonfly Array cannot see them? This is not a hypothetical question. Cosmological simulations predict that the universe should contain a vast population of dark matter halos that never formed any stars at all. These are halos that were too small, or too unlucky, or too exposed to the harsh radiation environment of the early universe to ever ignite star formation. They are completely dark, completely invisible. They contain no stars, no gas, nothing that emits or absorbs light. And yet they have mass. They have gravity. They orbit within and around larger galaxies and galaxy clusters, tugging on things, perturbing orbits, influencing the evolution of their more luminous neighbours. We have indirect evidence that these invisible galaxies exist. Around our own Milky Way, astronomers have detected streams of stars, long thin ribbons of stars that were pulled from disrupted dwarf galaxies as they orbited through the Milky Way's halo. These stellar streams should be smooth, unbroken ribbons, but some of them show gaps and distortions, as if something invisible has punched through them. One particularly well-studied stream, called GD1, shows a prominent gap and a spur of stars deflected off the main stream. The most compelling explanation is that a dark matter subhalo, a completely invisible clump of dark matter, passed through the stream and gravitationally perturbed the stars. If this interpretation is correct, then we are seeing the footprint of an invisible galaxy, a galaxy with no stars, no gas, nothing but dark matter, that exists in the halo of our own Milky Way. The implications are staggering. If the simulations are right, the Milky Way should be surrounded by thousands of dark matter subhalos. We see about 60 satellite galaxies. Where are the rest? They might be completely dark. They might be out there right now, orbiting around us, invisible, undetectable except through their gravitational influence on things we can see. The universe might contain far more galaxies than we have ever counted. Not galaxies of stars, but galaxies of darkness. Dragonfly 44 might be just the tip of the iceberg, a rare case where an almost completely dark galaxy retained just enough stars for us to notice it. Below it, in the darkness, there could be an entire population of truly invisible galaxies that we have only begun to comprehend. If this is blowing your mind, and I hope it is, do me a favour, drop a comment right now telling me what you think dark matter actually is. I want to hear your theories, your ideas, your wildest speculations. And if you are enjoying this deep dive, this is the kind of content we do here, so hit subscribe and let us keep exploring the universe together, because we are not done yet. Not even close. Let me now talk about something that has been simmering beneath the surface of everything I have told you so far, an alternative that refuses to die, an idea that some very smart people think might eventually replace dark matter entirely. It is called MOND, Modified Newtonian Dynamics, and it was proposed in 1983 by an Israeli physicist named Mordechai Milgrom. Milgrom's idea was radical in its simplicity. What if dark matter does not exist? What if the reason galaxies rotate too fast and clusters seem too heavy is not because of invisible mass, but because we do not understand gravity as well as we think we do? Specifically, Milgrom proposed that Newton's second law of motion, the foundational equation F equals ma, is not exactly correct at very low accelerations. In our everyday experience, and even in the solar system, accelerations are relatively high, and Newton's law works perfectly. But in the outer regions of galaxies, where stars orbit at enormous distances from the centre and the gravitational acceleration drops to extremely low values, Milgrom proposed that the relationship between force and acceleration changes. At these ultra-low accelerations, a smaller force produces more acceleration than Newton's law predicts. The effect of this modification is that stars in the outer parts of galaxies orbit faster than Newton would predict, exactly matching the flat rotation curves that Vera Rubin observed. MOND is remarkably successful in one specific domain. It predicts galaxy rotation curves with extraordinary precision, often using just one parameter, the total visible mass of the galaxy. In some cases, MOND predictions match observations better than dark matter models, which typically require additional fitting parameters. MOND also naturally explains a tight empirical relationship called the radial acceleration relation, which connects the observed gravitational acceleration in galaxies to the acceleration predicted from visible mass alone. This relation is tight, with very little scatter, and MOND predicts it automatically. Dark matter models can reproduce it, but only statistically, not as a fundamental prediction. But MOND has serious problems. On the scale of galaxy clusters, MOND does not work. It reduces the amount of missing mass compared to standard Newtonian gravity, but it does not eliminate it. Even with MOND, galaxy clusters still seem to require some form of unseen mass, perhaps in the form of massive neutrinos or some other baryonic component. The bullet cluster is particularly challenging for MOND because it shows mass separated from visible matter, which is difficult to explain if there is no actual invisible mass. And then there are galaxies like Dragonfly 44 and DF2. Dragonfly 44, with its 99.99% dark matter fraction, is deeply problematic for MOND. In MOND, the apparent dark matter in a galaxy is not a separate substance. It is an illusion created by the modification of gravity. The amount of apparent dark matter should be directly and unavoidably linked to the amount of visible matter and its distribution. You cannot have a galaxy where the modification produces an effect equivalent to 99.99% dark matter unless the visible matter is distributed in a very specific way. And the visible matter in Dragonfly 44 does not seem to be distributed in the way MOND would require. The extreme mass-to-light ratio of Dragonfly 44 pushes MOND to its limits. But DF2 is equally problematic, perhaps even more so. In MOND, you cannot have a galaxy with no dark matter, because the dark matter is not a separate substance that can be removed. It is a consequence of modified gravity, and modified gravity is everywhere. If MOND is correct, every galaxy should show the effects of modified gravity. A galaxy with no apparent dark matter should not exist, and yet DF2 seems to be exactly that. Now, MOND advocates have responses. Some have argued that the distance to DF2 has been incorrectly measured, and that if DF2 is closer than originally claimed, its mass estimates change and the discrepancy with MOND becomes less severe. This debate about the distance to DF2 went back and forth for several years, with different groups using different methods and getting different answers. The current consensus leans toward the original larger distance, which maintains the challenge for MOND. But the issue is not entirely settled. There are also more exotic alternatives. Erik Verlinde, a Dutch theoretical physicist, proposed in 2016 that gravity is not a fundamental force at all, but an emergent phenomenon arising from the quantum entanglement structure of spacetime. In his framework, what we interpret as dark matter is actually an effect of the entropy of the fabric of space itself. Verlinde's theory is mathematically sophisticated and makes some intriguing predictions, but it is still in its early stages of development and has not been tested as extensively as either dark matter or MOND. Another interesting idea is superfluid dark matter, proposed by Justin Cowrie and Lasha Bereziani. In this framework, dark matter is a real substance, but in the low temperature. High-density environment of galaxy halos, it condenses into a superfluid state. In this superfluid phase, dark matter develops long-range correlations that naturally reproduce the MOND phenomenology on galaxy scales. But on larger scales, like galaxy clusters, the dark matter behaves like a normal cold fluid, consistent with the standard dark matter predictions. It is an elegant synthesis of two seemingly contradictory ideas, but it requires specific particle physics properties that have not yet been confirmed. The honest assessment, as of the current state of the science, is that standard lambda CDM cosmology with cold dark matter particles remains the best overall model of the universe. It explains the cosmic microwave background radiation with extraordinary precision. It explains the large-scale distribution of galaxies. It explains the formation of structure in the universe from the smooth initial conditions of the Big Bang. It explains gravitational lensing observations. It explains the bullet cluster. MOND and its variants capture something real about galaxy dynamics that dark matter models do not easily reproduce. But MOND fails on larger scales, and it struggles with extreme objects like Dragonfly 44 and DF2. The resolution might be that dark matter is real, but that its behaviour on galaxy scales has some additional complexity that naturally produces the MOND, like phenomenology. Or the resolution might be something no one has thought of yet. That is the nature of science at the frontier. The answers are not always clean or satisfying. Sometimes the universe is more complicated than any of our models. Now let me take you back to the heart of this story. Let me take you back to the fundamental question that Dragonfly 44 raises. A question that goes beyond any single galaxy, beyond any specific model or theory, to the very foundations of how we understand reality. The question is this: what does it mean to live in a universe where most of what exists is invisible? Consider the cosmic inventory one more time. 4.9% of the universe is ordinary baryonic matter. That is atoms, protons, neutrons, electrons, the stuff of chemistry and biology, the stuff that makes stars shine, that forms planets, that build molecules and cells and brains. Everything you have ever seen, everything you have ever touched, every sensation you have ever experienced comes from interactions with this 4.9% of reality. The other 95.1% is, to our direct senses, and to almost all of our instruments, completely invisible. 26.8% is dark matter, something with mass and gravity, but no interactions with light, something that shaped the structure of the universe, but that we have never held in our hands or seen in our detectors. And 68.3% is dark energy, an even deeper mystery, a property of space itself that is driving the accelerating expansion of the universe. We understand dark energy even less than we understand dark matter. We do not even have good particle candidates for it. It might not be a substance at all, but rather a property of the vacuum of space. A cosmological constant that Einstein introduced and then called his greatest blunder, only for observations nearly a century later to suggest he might have been right all along. You are made of the rare stuff. Your body, the air you breathe, the food you eat, the ground you walk on, the sun that warms your face, all of it is made from the 4.9% minority. You are a tiny island of visibility in an ocean of darkness, and the fact that you can sit here, made of the rare stuff, and contemplate the existence of the overwhelming majority that you can never see or touch is one of the most remarkable things about being a conscious being in this universe. Dragonfly 44 brings this truth into sharp focus. It is a galaxy that exists almost entirely in the dark sector. It is a place where the invisible dominates so completely that the visible is barely a rounding error. If the universe were a novel, Dragonfly 44 would be a chapter written almost entirely in invisible ink. You can see a few words here and there, a few dim stars, a handful of globular clusters, enough to know that the page is not blank. But the real story, the real substance of what is there, is hidden from you.